How you doing? I'm Mr. Rose, and today we're going to tackle a nasty problem out of our textbook. Our textbook is ah, University Physics. Oop, there we go, University Physics, Young and Freeman, 13th edition, and it's out of Chapter 6, question number 102. Now I have, as I typically do, a little picture going on. I'd like you to read the question, but the summary of the question is we've got this crate that's had some initial velocity sliding up this hill at some angle alpha. Now, mu is not constant. They tell you mu, the coefficient of friction, is equal to some constant a times x. So it is distance dependent. They tell us oddly that the coefficient mu doesn't matter if it's moving or not moving. The coefficient of friction is always going to be the same. The other things they tell us is that the initial velocity is not zero. It does stop on this hill, so they tell us the final velocity is zero. And we're trying to prove what I have written here, that v squared is equal to this giant type of equation. So lots of things going on. The first thing I want to do, obviously, is draw a free body diagram. I'm going to put that right up here. Nope. I'm going to put that right here. My free body diagram. Got a force due to gravity going there. I've got a normal force. I'm going to label N. And I've got my frictional force going up the hill. Now you might be thinking, why is my frictional force going up the hill? Well, let me put a coordinate system here as well. I'm going to use this as my XY coordinate system. And I'm saying frictional force going up the hill because I'm going to examine the limits of this experiment. In other words, I'm going to say where it started with some initial velocity or some initial kinetic energy. I'm going to use the work kinetic energy theorem, meaning all the kinetic energy it has here, it is converted to the work it takes to stop the box from moving, or the crate, whatever's sliding up that hill. So it's equal to the work done by friction to stop this thing from moving. So since it's stopped, that's my examining point. So I know that the frictional force is holding it in place up that hill. Now this is my free body diagram. In another color, I'm going to add the components. Remember, free body diagrams and component diagrams are a little different, but I'm going to add, just for space, my F perpendicular and my F parallel. And I'll say that F perpendicular is the perpendicular component to gravity, mg cosine alpha. And I know F parallel is my parallel component to gravity. That is actually going to be negative based on my coordinate, negative mg sine alpha. So we're going to end up using those as we go. And now, again, I'm going to break this thing into steps, and then we're going to put it all together. The very first thing I'm doing, I already told you, is that we are going to use the work kinetic energy theorem. And that's going to become important. So we know that the change in work is equal to the change in kinetic energy. And since my final velocity is equal to 0, I really know, again, that we're exploiting those maximum points. How much work is done by friction is going to be equal to the kinetic energy of my initial kinetic energy. So for simplicity's sake, I'm going to say the work done is equal to the negative, because it's final minus initial, by negative 1/2 mv naught squared. So this is what I'm talking about. Now, we know we've said before that often we forget there are two sides to any equation, like F equals ma. We've got the ma side. We're going to use F equals ma later in this problem. And we've got the F side, the F net side. Here we have the same thing. We know that work is by definition a change in kinetic energy, but let's also not forget that work is equal to the antiderivative of F dot dr in my general sense. So I have my antiderivative of the force times the distance traveling up the hill. Now, this has caused some conversation of, shouldn't I be examining this as it goes up, because that force or the work is distance dependent? Well, it is distance dependent, and we're taking that into account with the coefficient of friction and when we integrate it, because that frictional force is doing work the entire way up. since there's no difference between kinetic and static friction, we can exploit this such that it'll be a little bit easier for us. Again, looking at those extremes, those maximum or minimum, so to speak. So that's what we're going to do, and I'm going to actually work with this side of the equation first, just because I think it's going to be a little bit easier for us. So I can keep looking at it. I'm going to rewrite, and I'm going to say work is equal to the antiderivative of F dot dr. And now, based on my free body diagram that we drew just before, I know that F is equal to really F net. That's going to equal to my frictional force, which I labeled FF on my free body diagram, minus, I'm just looking over, F parallel, which was mg sine theta. Sine alpha, sorry. Now, you might be thinking, whoa, isn't minus a negative? No, remember, I put it in as a negative based on my diagram. We always add components. So this would really be FF plus the negative mg sine theta. I'm just simplifying mg sine theta. So we have the frictional force minus mg sine theta is my net force. And now I'm going to plug that back into my work equation here, and I'm going to sub it all at the same time. So I'm going to say work is equal to the antiderivative of FF, which is going to be mu times my normal force minus mg sine alpha. I apologize, I keep changing alpha and theta, but mg sine alpha, where I know mu was given by ax, right? Let's recall the constant a times x, and we know the normal force is equal to mg cosine alpha. So I have the work done is the antiderivative of and I'm leaving out bad notation. dr is my general. This antiderivative, I'm going to have it as a dx because I'm using the x direction. So I have ax times my normal force, which is going to be mg cosine alpha minus mg sine alpha dx. So I'm taking the antiderivative of that entire thing. So this looks like it's a little complicated, but remember, most of these things are constants, right? I'm looking at the cameras, I'm sorry, the screen instead of the camera. Most of these things are constants. So this antiderivative is actually pretty simple. The only thing I'm taking the antiderivative of is this x and mg sine theta dx, this whole thing with respect to x. So work is equal to a as a constant, x squared over 2, right? That's the antiderivative of this. mg cosine alpha stays the same. mg cosine alpha minus the antiderivative of that with respect to x is just mg sine alpha times x, or we'd have x times mg sine alpha, and that is now my antiderivative. Gonna rearrange, pull things out. I'm gonna say work is equal to negative mg times, now I can pull that, ax squared over 2 cosine alpha plus x sine alpha. X times sine alpha. And that is the work done to stop the box up at the top of the hill. Now this x is going to come back to be a little bit of a problem. That was what I'm going to do towards the end of this question. Now the next part is actually the easier part, why I started with the hardest part. I know this whole thing, what did I do with that paper? I know this whole thing, there we go, recall, is equal to negative 1/2 mv squared, or mv naught squared, right? So now I'm just going to say negative 1/2 mv naught squared, that's good because I'm trying to solve for v naught, is equal to this negative mg ax squared over 2 cosine alpha plus x sine alpha. And now I can solve for that v naught. Rearranged, I can't make that easier, so I can get rid of those. I can say that's plus and that's plus. So I can say v naught squared is equal to, that m is going to go away, and that's going to be a 2 times a g times that whole conglomerate of things, ax squared over 2 cosine alpha plus x sine alpha. And I think I'm happy and I'm done, but those two things are definitely not the same. And what's not the same is what we started talking about. Mr. Rose, didn't I need to talk about that x? It was sliding up the hill. Yeah, we most definitely need to talk about that x. Sorry, I have my face over that. That's what that looks like. We definitely need to talk about that x. Well, what do I do with that x? Remember I said I'm looking at the max and the mins, like the extremes of this. So I know at the very top, my free body diagram, way up here, F net equals 0. I know that, not sliding down the hill. So what do I do with that? Apply Newton's laws, where A is equal to 0. That's super helpful, which means back to my free body diagram, I know that, what do I know in my free body diagram? I know the frictional force is equal to mg sine theta, right? So, or sine alpha. So I know FF equals mg sine alpha. And we've already made this substitution in for FF. I know FF by definition is mu times the normal force, mg sine alpha. Well, what's going on there? Let's get this normal force is mg cosine theta, mu is ax. Ax equals, oh, sorry, not equals. Ax times mg f perpendicular, mg cosine theta, alpha. Cosine alpha equals mg sine alpha. Do you see where we're going? Do you see where we're going? I think I see where I'm going. I got those guys out of the way. I can solve this equation for x in terms of constants. Very exciting. A equals, oh, that g is gone too. I don't know why I didn't cross that guy out. That g isn't there. I have A equals foolish Rose. I've got x equals. X equals sine alpha divided by a cosine alpha. And now I'm starting to look a little bit better. This is now going to get plugged into that conglomerate of a problem. Well, that is going to be a little bit nasty, but we're going to try and combine. All right, sorry, this is going to be something like a combining v naught squared. Am I still on camera? Yeah, v naught squared equals 2 times g. Put that down, put that into there. 2 times g times a. I'm going to factor that out. Yeah, I'm going to factor out the a over 2. Oh, which means the 2 is going to go away, but that's all right. I'll do that at the end. A over 2 times, now x is going to be sine alpha over cosine a cosine alpha. So sine alpha over a cosine alpha. That whole thing is squared because that x squared. Then I've got another cosine alpha. Then I've got a plus another x, so plus sine alpha over a cosine alpha. Gotta move that down so my face is out of the way. There we go. Times other sine alpha. So times sine alpha. Whew. That is an ugly, ugly math equation, but we start to cancel things out. I can cancel out, bring that through. That'll be V naught squared equals, the 2 is going to cancel. That goes with that. That's easy. So now I'm going to have a G out there. I'm going to have a sine squared, G times A. All right, so mess that up. We're going to have a G, A squared, and A. So, sorry, A squared is going to be there, A is up there. So that A is going to go. That's going to be a sine squared. So I'm going to have a G, do that, sine squared alpha. That cosine squared is going to cancel with that, divided by that A squared is going to cancel one of those. So that's just going to be an A divided by an A cosine alpha. Whew. Plus sine times sine is going to be sine squared alpha. Sine squared alpha over, oh, hey, look at that, cosine alpha. Hey, common denominators. I like when I have common denominators. That makes me look happy. That G should be on the outside still. I got to do one of those. So now I have my last step here. I can just combine. Oh, I canceled that 2 incorrectly. That 2 cancels there. That 2 should have distributed to there. So I should have had a 2. When I canceled that to that, I need to distribute that. So I would have had a 2 out here. Carry that 2. So now I have a 2 sign plus, so this is V naught squared equals, there's a G, there's a 2G, so I'm going to have a 3, a G, a sine squared alpha divided by A cosine alpha. And that is it. Let me compare. Did I do it right? Oh, this is exciting. The physics always tends to be easier than the calculus, but that looks like it works. Try and get all that on the same page here. Three G sine squared alpha over A cosine alpha. 3G sine squared alpha over A cosine alpha. Whew. That is all I have for you today. So just a quick recap of what exactly just happened is we had our free body diagram. I know it's being slid up the hill. It's going to slide up to the hill to the stop, so I'm going to exploit that I know all of the energy that went into friction. So I'm looking at that spot, the very end of my trip. I know it's distance dependent, which is okay because given information, mu is equal to did I not write that down? That mu was equal to AX. Oh, right there. Mu is equal to AX. I don't know how I missed that. So I know that. I used my work kinetic energy theorem. I started with work. I got the where is it? I got my work formula. Here we go. All of the work done to stop it. I compared that to the kinetic energy, which was 1/2 mv squared. Then I just started substituting numbers. The important part was we know it stops. I shouldn't say the important part. I know it stopped, so I exploited F net equals ma. I knew my forces were equal at the very top to find that in terms of x. And then we had 2 equations, 2 unknowns, where we did some algebra to get to the end. That is all I have for you this afternoon. Please feel free to like, click, or subscribe. Please feel free to comment, and you will see me here doing some physics next time.